Next speaker is Dr. Jino George. He's an upcoming young dynamic researcher. He is from Mohali, and he received his PhD on chiral plasmonics in 2012 from CSIR NIST Toronto. Later, he spent 5 years in Professor Abisson's lab at the University of Strasbourg, France, as a postdoctoral fellow, where he studied the effect of strong light-matter interaction on chemical and physical properties of coupled molecules and materials. At Mohali, his studies are focused on understanding the properties of hybrid light-matter states and its application in controlling chemical rates. He's also interested in studying the transport behavior of electromagnetically dressed 2D materials. Dr. Jino recently bagged prestigious Asian and Ocean Photography Association APA Young Scientist Award 2021. With this short introduction, I invite Dr. Jino for his presentation.
Thank you, Dr. Sajid. Am I audible?
Yes.
Okay, let me share my screen. All right. Thank you for your kind words of introduction. So I would like to thank Dr. Reggie and Dr. Kavita for giving me this invitation. And I especially thank Professor Pradeep for initiating this program for talk to open to college students who's been exposed to advanced research. I have a special reason to say this. Why I'm saying this, because it happened that in my college time, in 2003, I happened to attend one of the conference in Farook College. 2003, which was conducted by FCPS, if I'm correct. Listen to leaders in the country talking about advances in the science. The same year, I happened to listen another talk in NIT, Calicut, 2003, long back. At the time, the opportunities were limited. That triggered my interest to do some research. I mean, that's why I'm here. So that's something which is great and unique that Professor Pradeep and the management of Farook College is doing to encourage young students to come into science and exploring science and become potential future scientists or explorers for the country. Great. So I am seeing a large number of students attending. So you can stop me in between if you have any specific doubt. I'll be very happy to answer whichever way is possible. Okay, so we are a small group currently working in Mohali in Punjab. So our area of interest is controlling basically molecules and material properties by coupling to confined electromagnetic field. So today in this given, I have roughly 35 minutes if I'm correct. So I will be talking about a new concept that we developed in our lab. It's called cavity catalysis. We are introducing it as a new route to control chemical reactions very precisely. Okay, so my idea is to bring you the basic understanding. It's a new area of physical chemistry. Then it will slowly, it's more or less I can say photochemistry branch. Then I will explain you the fundamentals partially, and then I'll show some of the examples that we are doing in our lab. All right, so let us start. You are, I think, much familiar. I think you are a student of BSc or master students, will be most of them. I don't know exactly how much you learn about how a molecule absorbs. I am showing a very simple schematic, as you can see here. This is an energy nuclear coordinate. We can call it potential energy surface, but this is drawn in terms of a simple harmonic oscillator model. You can see that, if we take a pointer, you can see that here electron cloud in the ground state getting excited through the Frank quantum transition to the excited state. then it relaxes to the lowest excited state, which we call E here, and then it falls, or it decays non-radiatively, right? This is what happened in a molecular system. I'm considering this as a two-level system, as you can see here. So I am very much interested in this event, which we call absorption of a molecule, which is nothing other than the probability of excitation of the ground state electronic cloud to the excited state and then coming back. So this event is an oscillation, right? It goes up, come back, and goes up and come back. It's a very dynamic process. Great. And also please note that I mentioned 10 attosecond, which is a very fast process. This process happened very, very fast. All right, so I will try to connect this process to something called transition dipole moment, which is actually the probability distribution between the ground and excited state in which they are separated by a distance r and a charged q. So transition dipole moment will define the strength of a molecule for its absorption, right? This I think you will come to know later if somebody up North learn, but this is nothing other than the oscillator strength. A U-pact defined as absorptivity or molar absorptivity, epsilon. That means the ability to absorb light. So what I do here, I take a molecule one, which has a given energy, the same molecule, another one. Okay, so I can call M1 and M2 here. They try to interact through their transition dipole moment, D. What happens is due to this interaction, there is something called splitting of its energy level. Like you're bringing two orbitals together, you get a bonding and anti-bonding orbital. Here symmetry plays a role, you get a high energy orbital and a low energy orbital. But more interesting, I was telling you this dynamic process, photon is being exchanged between this state to this state. It's like a ping pong game. It goes from here to here, here to here. It's like this process happened in femtosecond time scale, very, very fast. All right, and that creates this interaction V, which goes as like D square, which is the transition dipole square divided by the distance separating the dipole. Okay, there are other things, symmetry rule comes in there. This is a basic picture of it. What will happen here is that due to this process, your effective dipoles increases dramatically. For example, a molecule, this I've mentioned cyanine is TDBC, it's a cyanine dye. Cyanine dye is a special dye because their ground state conformation and the excited conformation, they are similar. That's called cyanine limit. Maybe Anne Schumann, who presented just before Professor Robin, was an expert in dealing with that. So cyanine dye is a special class of dye in which their ground state and excited state, they look similar. What will happen is eventually their transition become vibrationless. That means your vibration level simply disappear. You will have a beautiful transition from 0 to 0 of ground to excited states. Their Frank quantum state becomes 0 to 0, become vibrationless. That results in an enormous increase in the dipole strength. We call transition dipole increase to something around 10 dBA to 12 dBA. Okay, a normal molecule has something around 1 or 0.5. That results in a molar absorptivity increase of roughly 1 million or more. So that roughly TDBC has a molar absorptivity coefficients of 10 power 6 centimeter inverse per molus. So it's a beautiful system. So what I will do here, this is known like in chemistry, you can create aggregates, right? So when molecule A mixed to molecule B, molecule C, etc., ABC, they all come together from chains or different kind of structures. This is called supramolecular chemistry. Right, now let us think about changing one of the molecule by an optical field. Here I have matter resonance, which is your molecular state. You see this molecular state here. Then I replace one of the component by an optical resonance. The minimum criteria for this is that the optical resonance should have a matching frequency to the matter resonance. They are in same energy, you see here. So now I am replacing the previous one, this particular molecular resonance by an optical resonance that undergo the same kind of interaction. Okay, so I replace very clearly a matter component by optical component. So you have light interact with matter. So optical resonance means my photon confined very tightly. One of the configuration that we used is fabric parod cavity, which is shown here. It is a simple configuration. This is one of the simplest configuration that we use in our lab. Here what happens, the photon comes from here. that will penetrate through the mirror. We allow some light to travel into and then undergo multiple interferences inside, create standing wave or photonic field. Okay, the minimum, which is lambda by 2, then lambda, 3 lambda by 2, goes on like that. So you create a fabric proud cavity modes that is nothing other than stopping light for some times inside this particular geometry. Okay, so you get a minimum energy, which is lambda by 2. According to Heisenberg uncertainty principle, you form lambda by 2, which is actually, you cannot define the position and energy. So you get minimum energy, which is called the 0-point energy of this particular cavity. Same thing molecule also process. You already studied maybe in your master degree what is 0-point energy of a vibrational state, which is half h. Right? So what I am doing is an exchange of interaction between the matter state, or say photon excite this matter, it goes up here, this come back to undergo this again, ping pong game, split the energy into two, one upper and one lower. Similar like I've told before, hybridization process. So what fun here is this interaction goes as d into e. The previous one was d squared by r cube. This goes as d into e, where d is the transition dipole moment, e is the electric field. Electric field will be defined. Maybe I will skip that explanation, but this is how it comes from. It's a photon E field into a term which is called the vacuum field, which I was explaining, half h nu, or say here in the case of photon, which is lambda by 2. That means I can have an interaction acting on the system even in the absence of photon, external photon. You're dressing a molecule by a field by doing this. All right. So another interesting feature, this interaction energy we call E, which is nothing other than Rabi interaction. Rabi interaction is, you can see that oscillation. A photon goes from light state to cavity state to the matter state and come back and go back and forth. This is called Rabi oscillation. So I'm not going into those details, but what happens is if you increase, instead of one molecule, you bring 2, 3, 4, and the n number of molecules, say Avogadro number of molecules, what will happen is that the splitting energy increases. That goes the square root of concentration. So we get a reasonable splitting in the system that will redefine the entire properties of the molecule. Not only that, I create a state which has half molecule, half matter, half photon. That means it has a hybrid nature. Then a photon is interacting not with one molecule, it is interacting with n number of molecules. So you can create a coherent state through that photonic degrees of freedom. And then you get dispersive behavior, which is called energy momentum relation. I remember Anshuman was showing some experiment which you have energy momentum relation on the K space, which is the lattice space. Here I am getting on the photonic space. Okay, that's more of a way of saying it. That means I am having my matter state is half molecule and half matter, a new form of light. They're called quasi-bosons. Right? They even exist in dark, so I can play. I don't need an external photon. I can do something with that. That's coming from the vacuum field, which is called the 0-point energy or vacuum fluctuation, this idea. I'm not going into those details, but I will go directly what we are doing in maybe another 20 minutes. So this is a new branch of physical chemistry. In our group, we will be working on a problem that we can control chemical reaction by using this concept. Another aspect of studies on material science, how you control transport in behavior. Professor Sambut was showing you some experiments, right? Electrochemistry. For example, I can put an electron into such a coupled state, then I can look into their coherence, how the transport is occurring. Then another part of my students is working on advanced spectroscopy, looking into what are the properties of these polaritonic states. All right, so let us start with polaritonic chemistry. So this concept of coherent chemistry, first of all, what there exists almost a couple of decades, 3 decades at least. You see some of the old paper from George C. Pimentel, who was from Berkeley, okay, proposed that he was a pioneer. He basically made a carbon dioxide laser, and he was also the one who basically behind the matrix isolation setup. Okay, that people use very low temperature studies with trapping molecules, atom in that. So he has a special state-of-the-art facility there studying the properties of system. So he showed actually that you can have, for example, this particular reaction CH2 interact with fluorine, form an adduct. He tried to invoke some particular vibrational states, some particular vibrational state, and specifically look into the rate of the reaction, conversion. This here you have psi, conversion rate versus time. So when he shine carbon dioxide laser, suppose I shine light of 3100 at 0.5 centimeter inverse to that particular reaction, you see the rate of the reaction is boosting, increasing, enhancing. That happened to dumping of energy to the bond and bond breaking. And just before that, I also forgot to show this particular example shown by these Bell Laboratory teams. Okay, this is an experiment with H2 plus molecule. They use a molecular ion and ionize the system, very high energy. Okay, this is another interesting concept that people used before, like terawatts power of energy, and bump into energy of these states. And what happens is that your electron cloud will move because of the oscillation of the field, but nucleus cannot cope with it. So what happens is the system simply break. So I can break, I can simply open a well, a potential energy surface. Then what happens is that molecule break. So this is actually was there, and what happened, the main problem with this coherent chemistry approach, there are a lot of people worked on this. Okay, one of the review you can read from Richard Serre has been written a beautiful review in 1998 about this, how coherent chemistries can be used. Richard Serre has contributed a lot of this into this particular field. Okay, so what is happening is that a very high intensity field people are using to do. Light approaches the internuclear binding energy of molecule, the molecular potential deforms, and you get a bond softening. But what we have done, I mean, I happen to be lucky to one of the students of in 2012 working with Thomas Eberson at the University of Strasbourg, who introduced this concept that I can have this experiment conducted without an external source. We don't even use external photon. The geometry itself create the vacuum fluctuation, the dressing of the state happens. So I can do the same experiment without having all these complicated setups of laser. I can do it in a small, I will show you that in a few minutes. So we use either low intensity light, which is basically there are some argument going on, or I can have vacuum field coupling and modifying the energy level. So that is how it's called strong coupling chemistry. So this is our first paper, which came from a person groups in 2015, that we've shown that a particular vibration, you have, I think you are familiar with, I think in your BSc level, you will be introduced to the book of Barnwell. I think there you have studied a vibrational, vibration states, right? Vibration states or vibrational rotors and other things you have studied. I'm sure part of you at least. Right. So what is V0? V0, I said this is half H, which is the 0 point energy of the system. The fundamental transition is V0 to V1, as you can see here. Then what happened when we tune? So here this is one of the representation of a cavity. I have actually a germanium substrate, which is IR transparent. Then I put a mirror over here. I sputter or evaporate a mirror, very thin mirror. It will control the light flow into it and then create a mode with, and then again you spin coat some material. Here this is polyvinyl acetate. This is actually some concept proposal paper. We basically took polyvinyl acetate, which has a very strong, sharp carbon stretching band, as you can see here, and then dispersed in it, and then bring another mirror. Okay, when you close the system, you get a standing wave. We tune the distance between these two mirrors so that the standing wave matches this frequency of this fundamental transition, and you get the splitting. Okay, this is creating vibropolaritonic states. So we use it. So this is the geometry that we use in our laboratory, that been improvised form of it. And you can see that this is how small it is, like 3 centimeter long, small cell, which we created, which we generally make ourselves in this cell in our laboratory. We will inject the solution. If there is an inlet here, the solution goes inside, and then you will tune the distance between, this is a one mirror gold and a second mirror here. There is, this is on BF to Minto. There will be silicon dioxide separating or protecting the mirror so that the molecule which is injected in A plus B, reacting C, for example, will not be interacting with the gold to avoid any catalysis by the metal. So it is pure glass, silicon dioxide coated. And then you will inject the solution, reacting mixture into it, and then it comes out. Eventually, you can either spectroscopically study them in situ, or you can complete the reaction, take it out, and analyze it. This is how a fabric probe cavity looks like. And you see how the modes are confined. I'm showing a fifth mode. Lambda by 2 is the first mode. You get a gradation mode, I think, that comes linearly here, versus linear scale. You can see that I'm having 5th mode, 6th mode, 7th mode, etc. Very sharp mode with a full width half maximum roughly of 20 to 30 low numbers. And we call Q factor, which is called finest factor of the cavity, is roughly 120 to 150. That's it. I mean, I can call cavity factor, quality factor, nothing other than I will have this round phase accumulation of the photon inside the cavity before leaking roughly 100 times or 150 times in these cavities. They are very lossy cavities. There are experiments people have done that they can stop photons like 1×10⁶ times. Then they can stop equivalent to milliseconds sometimes in some experiments. But in our case, we don't need it. We stops in some maybe picosecond to femtosecond time scale in the cavity. This is in reality. Okay, in this particular experiment. So this is the first experimental demonstration, which is again done in Epperson lab, that we took a molecule, this particular molecule. This is the reactant in which there is a carbon-silicon bond. Okay, this carbon-silicon bond is this particular vibration. We couple the field and create the polaritonic. You can see the P plus and the P minus band here, and look into this product. So what when this getting converted in the product, this band slowly disappear, right? Then what we'll do is that we look into, so this is how the flow will look like. So then we have, I mean, I already shown this. We've passed IR beam here, and then there is a detector, and we will look into the difference in the FSR, which come from the refractive index variation. This will be very sensitive because this mode will be very sensitive to refractive index. Okay, so if a small change like fractional change in the refractive index affected. So if the reaction, this product reactant convert into product, there will be change in the refractive index that will be plotted giving a first order plot. You can also do that if you take out the product and then check it. So you see that this was beautifully first order reaction. So you see that when you have off resonance or outside the cavity, if there is no mirror, the reaction rate goes like this. Okay. When you are off resonance with respect to
can you please elaborate a little bit more on that measurement? So you're passing an infrared beam which is polychromatic.
Right. So I will pass. I will just do FTIR. Do Fourier transform for infrared spectra. We will acquire a spectrum of this cavity mode as I shown here. So when the reaction occurs, first of all, this band will slowly disappear. Our coupling string disappear. At the same time, I can observe some of these higher order modes. What happens is that they are highly sensitive with respect to the index of the medium. My FSR, free spectral range, goes as 10⁴ divided by 2 into n into L, where n is the refractive index. L is fixed. So a small change in n will basically, we can calculate back how much product is formed. This is what we are doing in this experiment. So we calculated the change in FSR, which will connect to the reaction because it's a first order reaction. So anything you look on the window that's happening on the other side, you can see it because it's a first order process. So we look here, we use FSR, which is the free spectral range, which is an indirect count of the change in the index of the medium. Later, I will show you how I will do this experiment in the UV spectroscopy and other techniques. So this is the first experimental proof what we did. Then we took the product out. So we took the product out and we studied by GCMS. This is a kinetic experiment. Then final product has been taken out. And then we observed what happened. Like outside the cavity, you see that product is forming very fast. Inside the cavity, the product is forming very slow. You can see that this is a rate is slow here. So this was actually shocking to us. We were thinking that by coupling to field, I can able to control the reaction. In the sense, I can speed up the reaction. But in the first experimental proof, it shows that we are slowing down a reaction. So there are a lot of discussion happen. So I will come to that in the last part when we see more experiments which have been recently conducted. So this is another set of experiment. This is another set of experiment that I've done. So I was telling you this experiment, we are slowing down a particular reaction. In this case, we are catalyzing a reaction. So here we have taken a simple molecule PNPA, para-nitrophenyl acetate, and TBAF is a very mild base in ethyl acetate. This particular P minus, this is para-nitrophenoxide. This can be done in a normal UV spectrometer. You can measure the formation of this. I will show you this. What happened is that this is the carbonyl band of the ethyl acetate. And this is the band of the PNPA, para-nitrophenyl acetate. They match in frequency. Photon cannot discriminate one over the other. So what happens is that I'm taking 10,000 molecules of ethyl acetate and 1 molecule of PNPA in the system. Eventually, I get a coupling. I say that my coupling goes as curve of C. I get a coupling very large, literally in the system. Then I follow the reaction. You can see the kinetics beautifully. In a normal cell, it comes like this. But in the cavity, the moment I tune to on resonance, I'm seeing the rate is boosting very fast. At room temperature, we see more than 1 order of change in the rate of the reaction in the cavity. So this we repeated. This is called tuning experiment. So we have the flexibility. I can move the mirror manually. Okay, so distance between the mirror. You can see here. So the blue one here, this first point where one of the mode. This is the 10th mode position. I have to think this is the 10th mode of the cavity, which is sitting over here. I slowly move the mirror such that it comes to resonance. So now it is resonant to the carbonyl band. You see this reaction getting speeded up and getting 25 times or something like 20 times. And then you move away, it decreases. So the field is doing a wonderful job by coupling to the field. You remember the previous experiment here that I was showing you there is a coupling. What happened here, this experiment, the product, so the reactant is slowly diminishing. I was telling you my coupling strength goes as D into E, but here DE is slowly dying. The number of molecules is dying, the coupling strength is going collapsing. So that the rate comes back normal finally, because if there is no molecule in the last stage of the reaction goes normal as normal cell. But here it's wonderful that I can have the reaction in presence of solvent because solvent is not reacting. I'm only having the PNP reacting. So I do a cooperative coupling. So this is one. And we published this 2 years back, and it's been widely appreciated by the community. And now we are trying to understand. I mean, we have done more control experiments to prove this effect. That you can see here, there is something called Caherent equation. Caherent equation will basically come from Arrhenius equation and taking from thermodynamic factors. We calculate the enthalpy of activation as well as the entropy of activation of the system very precisely by doing temperature dependent experiment. We see that in the cavity as well as the non-cavity, you can see the change in the activation parameters. You see that there is roughly a change of 45 kilojoule per mole, okay, of enthalpy of activation just by coupling one vibration state to that particular reaction. So you can see here that's a change of roughly 10 kilocal per mole. It's a huge amount of energy, hundreds of multiples of kBT. So if it's a thermal reaction, so a molecule A is colliding with molecule B, it's a thermal reaction. So you have all the equilibrium process, still you have an effect which is triggering the process, and you see the delta G, which is dropping by 5 kilojoule per mole here. And we propose this like forming a kind of a more polar activated complex. This may not be correct. This is more like a chemistry terminology. But what happens here is that there are a lot of other aspects here that the reaction can happen to many other channels as well, like to form, I was just mentioning, a photonic degrees of freedom, which is created in the system, which we are still trying to understand. So we extended further this, again, another control experiment. What is one of the reasons why I'm saying that is still follow Arrhenius reaction. You can see that, but you see that when you increase the coupling strength, there is a nonlinear behavior. I'm seeing a quadratic trend to coupling strength versus rate of the reaction. This is log scale, okay? So you can see here, whereas the coupling strength is square root of C, we are trying to understand why this nonlinear behavior is happening, and most likely it may affect the transition state under strong coupling. This is another, I will show you one more case study in the last example. Right, so we continue this concept because it's the first prototype experiment that we have shown in the lab. Okay, so that you can control a reaction by coupling to field. We have a lot of other control experiments. I'm just skipping them because of our time constraint. You can see here, this is the case, a simple ester hydrolysis. So ester hydrolysis in the presence of an enzyme alpha chemotrypsin. So here the same concept, I use a solute, which is alpha CT, water as a solvent instead of ethyl acetate in the previous case. I am skipping the mechanism, but what happens is you couple water, which is in large excess, and your molecule which is your ester, which is your enzyme, which is controlling this process through some triad formations of a particular mechanism to convert PNPA into PNP minus. We study the same kind of substrate in this experiment. What happened eventually, you couple the OH stretching band to the cavity field and study the properties. You can see here that very clearly when you couple, this is nothing other than a Lineweaver bulk plot. We plot 1/V versus substrate concentration. So this is when we plot this, we'll get actually something called turnover number and catalytic efficiency. We clearly see that the non-cavity experiment shows a beautiful straight line, which again clarify or prove we can extract the turnover number for the non-cavity something around 0.6068 minute inverse, whereas the catalytic efficiency is 248. Whereas in the cavity coupled situations, you see that the catalytic efficiency increased roughly 1 order for some times. And turnover number also not changing much, which shows that a competitive kind of a catalysis. Already you have a catalysis event. In the presence of field, you are doing a competition. So this is another one we have published very recently. And okay, these are the papers, which is the first paper. And we have, I'm showing you some of the news related to this concept. Right, so I have another 5 minutes if I'm correct. Can I take another 5 minutes?
Yes, yes.
Sorry. So this is the last one that we have just communicated, which is available in our archives, Chem archives. So this is done by a student, Tabassum Muhammad, and one of my PhD student, who actually happened to be in the last EFCS conference in 2019, who might have introduced this to the community. Here, what we have done is actually we took this molecule, this particular molecule. It's a slightly different. It's PNPB instead of PNPA. So this is again a leading group is pyranitrophene oxide, but we take different derivatives of phenyl. This particular benzoate is substituted different derivatives, and you can see here that very precisely by changing the substituent, you can follow their particular the rate versus sigma. So this is okay. Sorry, this should be smaller to k. So when you plot the ratio of the rate of the substituted by unsubstituted versus sigma, which is sigma is substituent constant, which comes from the equilibrium constant, which is basically defining between benzoic acid and benzoate ion. So that is a constant value we took from the literature, and we plotted that this is non-cavity situation. You get a rho value, which is the reactivity constant. Okay, so this gives a straight line. What we did was when we coupled this to cavity mode very precisely to the cavity mode, we found that it's simply deviating. It simply deviates from the so-called Hammett relation. This is the Hammett relation. I think you also might have studied this. Students are familiar with this, I hope. So, so what we have done, we have taken a common axis, sigma, because we are not sure the equilibrium is getting shifted. That is our assumption. And then we calculate the rate change with respect to the true system, as you can see here. So in the non-cavity, it's a straight line. We get a linear relation, whereas in non-cavity, we get a non-linear relation. And the corresponding rates are given. We get for cavity, we got two rho values. One is negative, one is positive. That we thought that it redefined or changed the mechanism, but the mechanism has not changed much. We still get an isokinetic behavior. That means when you plot delta H versus delta S is still getting a straight line, which indicating that something is happening thermodynamically that modify the transition state. So we are under this is under revision, this paper. We are also doing some other experiment to prove that what is happening in the thermodynamic compartment. So it's really reshuffling. You can see that it's really reshuffling, especially delta H and delta S across like a normal catalysis event. So free energies are changing due to this effect, and then you have a catalysis, or if it is free energy is increasing, that will basically be an anti-catalysis event. That's what might have happened in the previous case. It's the same thing. They have seen a free energy increase, like something around 3 to 3.5 kilojoule per mole in the first experiment proved by a person group. And here we are seeing a free energy dropping, get a negative value. We are also seeing some cases it's not changing. I'm not presenting those details, but this is what we are ending up in saying that There are two things with symmetry of the field interacting with the field and the transition state, how does it couple with the field. This is actually more complex to theoretically simulate. I would say the theory is much behind experiment to prove it, because we have to consider now how the photon is dressing the state in this particular case. Anyway, there are a lot of warm discussion going around the community for understanding this particular behavior. So far, this many molecules been tried. This is the first experiment tried by a Boston group. And you can see this is the experiment that we have tried 2 years back and our recent work. And there is another work from a Japanese group, Hirai from Kozhikode. They also published a print cyclization reaction in similar direction. Then there is, I was telling about the symmetry rule. This is another work. So there are only few works which are available. There are also maybe 1 or 2 reviews available so far in this particular field. I would like to conclude by saying this, that when I say that our field can be connected to photochemistry, but the idea is coming from vacuum fluctuation. But you have to think about in photocatalysis, the photon is getting consumed, which is again a representation that you're consuming again photon, you have conservation of energy. Here also you conservation of energy. I'm not going out of the conservation energy process. You have virtual photon, which is doing the process here. So we are following an uncontrolled path to control. And most important thing here is that I'm just coupling a vibration to control the reaction. That was a dream for physical chemists for decade. That experiment of George Pimentel and Mohammed El Says and so many people tried long back to prove that use of coherent chemistry to control reactions. So maybe this may be opening us new channels, like I can have a site selective, mode selective coupling possible that will trigger some special kind of reaction control understanding of the reaction mechanism. Again, we are also proving the existence of zero-point energy. So, okay, this is another line. Currently, we are also working on some other aspects of this problem. Like Professor Sampath was explaining you that we can study transport of properties, transport properties of molecule coupled to the field. One of the field is polaritonics. We are also working in this area. This is my group. I thank mainly Jyoti Ladar here. She is actually mainly contributed. Akila partially contributed this program, and also Pooja also. These three basically. Jyoti is this is mainly on this problem I just presented. I also thank Professor Thomas Epperson for initial collaboration. I also thank Isa Mohali, Minister of Education, SCRB, and STARS for funding. Thank you. Happy to answer your questions.
Thank you very much, Dr. Jino, for your introduction, for interesting talk on a new area of physical chemistry. Now it's a time for a discussion.
Well, very nice talk. Let me just start by asking one question. Maybe others will follow. Strong coupling is giving new chemistry, catalysis, maybe possibly photochemistry, or the way to look at photochemistry differently, all that. I was thinking that there's a lot of excitement today happening in confinement. After all, this is an issue of confinement. So one kind of confinement induced chemistry that is happening is in droplets. I spoke about yesterday. And these droplets are of micrometer dimensions. I wonder whether it is possible to induce chemistry by the kind of thing that you are talking about, not necessarily the way that droplet scientists have been looking at. So can confinement be, the strong coupling be responsible for some interesting phenomena seen in droplets?
Right. Okay. Thank you, Professor Pradeep, asking this question. Unfortunately, I could not join yesterday because of some selection committee problems here. So I had a long discussion when Professor Richard sir visited us 2 years back to our campus. So, I mean, you may be familiar with one of his experiments that he tried to do.
Yeah.
Try to convert water into hydrogen peroxide, one experiment that he was presenting. So this experiment is something very interesting, that the droplets on its surface will show very high, what you call, potential differences. So I'm not sure how electromagnetic will do it, because it's anyway a three-dimensional problem. I am now talking about a two-dimensional problem between the mirrors. So
in the dimension of a molecule,
right,
all these droplets are all two dimensions.
Yeah, so the whole problem is that I have to have a standing wave, and if I take a three-dimensional sphere, I will get a cavity mode exactly in the center where the node is. So when I do simulate it, I will not get electric field everywhere, but I get in the center. So that is my problem. I don't know how about the periphery, which is hard for us to do by doing a simulation, because we always do some simulation when we see that how the field is distributed. That is easy for us. So maybe it's worth looking into how, when you think about a droplet, how will be, if suppose a photon get trapped in that particular geometry. Anyway, it's a game of index variation finally when I am stopping light. So if I can create a photon in a droplet, but you can think now everywhere, I mean, it's like a spherical drop, right? So I'm not sure how does it like the field distribution look like. The maximum will be in the center and the periphery will be minimum. So that's all my problem. But anyway, very interesting. That's actually that I was also excited after seeing the talk of Professor Sayre, and I will go back and check your talk. I mean, listen to your talk as well regarding this.
Thank you.
Thank you very much.
Sir?
Yes.
Yeah. I have a doubt.
Yeah, please.
Like, can we use like you use the silver mirror or gold mirror? Can we use both?
Right, yeah, no issue, because what we do normally, so I didn't explain those technical details. So you can use silver mirror, but I would suggest gold or aluminum, which are they are more stable than silver. Silver oxides much faster. So these are very thin mirrors, roughly 30 or between 10 and 30 nanometer. What happens is that when you do reactions, even you have a silicon coating on top of that, these mirrors slowly simply etched away or oxidized away. So silver has a high affinity to get oxidized. So I prefer gold, which is normally a stable system. So that's why we will use gold in our experiments and give very good reflectivity.
Yeah. Okay, sir. Okay.
Any other question? If there is no other question, let me ask you, can you explain the deviation in the substituent effects under this cavity environment?
Can you repeat what?
There is a deviation in the substituent effects. So you showed the nonlinear curve.
Right.
So can you explain that? Why it is happening?
So we are also understanding why. I'm not sure exactly, but what we proposed in the paper that there is actually. Am I audible?
Yeah, definitely.
Sorry. So what we proposed in the paper that across the aromatic ring there is an internal vibrational relaxation path which is getting opened and killed by the cavity system. This is the one we proposed, which is more or less getting clear. Maybe some theoretical experiment is doing by Professor Srihari from IIT Kanpur. Currently, he is interested in this problem, but we are not exactly sure because there is no theoretical model available so far. So this is interesting, but it's very clearly that deviating. So we think that there is some, some vibrational channel which is basically controlling it. Like internal vibrational channels.
Okay.
Because anyway, the energy flow which is happening from the substituent to the reaction center through the benzene ring. So this channel is either boosted or being shortened. So
any modeling studies in this area?
This is quite difficult as of now because so far people have tried. There is a group in Hamburg. They tried actually H2 plus molecule. That's the best that they can do on field coupling because there's something called quantum electrodynamics coupled to density functional theory, which is quite hard to understand how the potential energies look like. So large molecule, if you take, it's very difficult. So that's why I'm saying experiment is much ahead of theory. So maybe in future.
Any other question? So once again, I thank you very much for accepting our invitation and please accept our memento. it's not visible.
Thank you, Sachin. Thank you very much.